Hi. Welcome back to my channel. And this is our third lecture on isomerism. And you know that actually we are discussing about the tautomerism. Already few examples are completed in the last lecture. In this video lecture also, we are going to discuss with very great examples. And these examples are very important for mains and advanced right now. Okay. Here I am going to take first example 1,3 dicarbonyl compound. It's a very great example and very important. 1,3 dicarbonyl compound. Yes, this is our starting example. We know that every molecule under isomerism, they are having same molecular formula. So in tautomerism, how we are producing the tautomers, structural isomers, okay? So tautomers are produced by oscillation of hydrogen atom or movement of hydrogen atom, sometimes from 1 to 2, 2 to 1, and sometimes from 1 to 2, 1 to 3 and 3 to 1. So if it is oscillating from 1 to 2 to 1, so what is the name of that system? Diode system. And if your proton is oscillating from 1 to 3 and 3 to 1, what is the name of that system? Triad system, right? So by the oscillation of hydrogen or by the oscillation or movement of hydrogen, so we are producing tautomers. Very clear. And one more important thing, sometimes we are observing that same molecular formula and we are writing equilibrium between the molecules like keto form and enol form. Why sometimes keto form is more stable than enol form, and sometimes why the enol form is more stable than keto form, okay? And how sometimes the equilibrium constant value is greater than 1 and sometimes that same equilibrium constant value is less than 1. What are the reasons? Now these we are explaining on the basis of aromaticity, then hydrogen bond strength and extended conjugation, and on the basis of a bond angle strain also. So one by one we will discuss each and every example. So once again you remember that this class is very important, right? So what is our first example? 1,3 dicarbonyl compound. Sir, I want to write enol form of this compound, and here question is, so where from I should select the proton? So on the basis of general organic chemistry, you know that once there is a 1,3 dicarbonyl compound, here you have two acidic protons. Where from you are selecting that acidic protons? Yes, here one type of acidic proton is present, okay? Right side also same thing. These two protons are equivalent, equal acidic. And middle carbon atom, yes, here also two hydrogen atoms are there, okay? For clarity I am taking like this, A protons and these protons are B protons. So where from we are selecting proton? That's very important. Yes, we are selecting proton from B. Why? What is the reason? The reason is actually acidity of acidity of any acid. So either carboxylic acid or alcohol or active CH, anything. Acidity is directly proportional to stability of anion. Acidity directly proportional to stability of anion, okay? That's very important. After removal of proton, if stability of anion is more, then acidic strength of that particular species is more. That's very important, okay? Right. Acidity is directly proportional to stability of anion. And from general organic chemistry, we know that after removal of proton from middle carbon atom, right? If any CH is planked between two electron withdrawing groups, right? This one electron withdrawing group, again this carbonyl also electron withdrawing group. If your proton is planked between two electron withdrawing groups, that CH is taken as active CH. What is name of that CH? Active CH. Active CH nothing but this CH acidic strength is more when compared to left side CH as well as right side CH, okay? Now this one is taken as active CH. So based on acidic strength of that CH, in order to write enol form of this given compound, particularly I am selecting proton from middle carbon atom. Yes, selection of proton completed, right? So now how we are writing the enol form of this compound? That's very simple, right? Here by shifting of CH sigma bonding electrons towards this carbon atom, okay? Right. And shifting of pi electrons towards the oxygen atom. Very clear. Now here how to write the enol form? Left side you don't disturb that keto form. Yes, fine. Here introduce new pi bond. Yes, very clear. Methyl. And here what we are writing? OH. This is our enol. Okay. Now we will discuss at equilibrium state. Now who is more stable and what are the reasons? Right. First you think about the 1,3-dicarbonyl compound. So in case of 1,3-dicarbonyl compound, yes, carbon has partial positive charge, oxygen partial negative charge. Here carbon partial positive charge and oxygen partial negative charge. For example, if you are thinking about if you are thinking about dipole-dipole repulsions, actually here there is no problem with dipole-dipole repulsions. Why? What is the reason? Yes, there is a conveniency. This molecule can undergo CC bond rotations easily. It can escape from the dipole-dipole repulsions. That's why there is no problem. But why that ketone form is converting into the enol form? Sir, what are the advantages of that keto form in enol form? What is the reason for converting keto form into enol form? That we will see now, right? Now, just to observe these two, keto form and enol form. What is the first advantage? For example, if you are asking that, now enol form, it says that, sir, I have conjugation. Two double bonds are separated by single bond. Pi, sigma, pi. Enol form says that, sir, I have continuous conjugation. I have conjugation between these two pi bonds. What is the advantage of conjugation? Conjugation always stabilizes the molecule. Yes, that's why enol form is stable. That is the first reason. Same point I am writing here. It has conjugation. It has conjugation. Very clear. And come to the second point. One more advantage also there. What is the second advantage? Along with the conjugation, there is intramolecular hydrogen bond. Intramolecular hydrogen bond. It has intramolecular H bond. H bond nothing but hydrogen bond. Intramolecular hydrogen bond. Okay. So that is very clear. Once again, here we have keto form and enol form, right? So we want to explain equilibrium constant value, y greater than 1, y less than 1, y approximately equals to 1, like that. Okay. So just you look at the molecule and take advantages and disadvantages, automatically you will get the idea. In enol form, two advantages are there. What are the two advantages when compared to what keto form? Yes, it has conjugation. Two pi bonds are separated by single bond. And it has H bond also. Intramolecular hydrogen bond. Intramolecular hydrogen bond. These two are the stabilizing factors. That's why now equilibrium more towards enol form and less towards keto form. And if you are going to express that equilibrium constant value, yes, equilibrium constant it equals to concentration of enol by concentration of keto form. And we know that here concentration of enol is more when compared to keto. That's why what is the equilibrium constant value? Greater than 1 or less than 1? Exactly, it is greater than 1. Okay, so very, very important. In case of 1,3 dicarbonyl compounds, enol form percentage is more when compared to keto form at equilibrium. That's why equilibrium constant value is greater than 1. For example, theoretically, if they are asking any points about the enol form, you select these two. What is first one? It has conjugation and it has intramolecular hydrogen bond. Very, very good example. Note down these 2 points. Conjugation and intramolecular hydrogen bond. Yeah, one more example. Same 1,3 dicarbonyl compound, right? Here I am going to take same thing, C double bond O, again C double bond O. But what is the difference when compared to previous example? In previous example, we have methyl groups left and right side. But here, just for a change, instead of now methyl groups, I am taking here phenyl groups. Then what is the situation, right? Yeah, phenyl groups are there. Very good, fine. That is our molecule. Again, I am going to write enol form of this compound, right? So every time there is no need to represent active CH. Directly I am going to write that enol form. From right side I am using carbonyl. For tautomerism, yeah, this is my molecule, right? Right side again there is a phenyl ring system, yeah. Here, just you look at keto form and enol form. Same as previous example here. Advantage is this molecule has very good conjugation. Even when compared to previous example, in previous example, there are only methyl groups. Okay. But in this example, yeah, phenyl groups are there. Oh, 1 second. Phenyl groups are there. Because of the presence of phenyl groups, conjugation is increasing. That means some extra stability is provided for the enol form. Okay. Look at this one. Yes. Pi sigma, pi sigma, pi sigma, pi sigma, pi sigma, pi sigma. It has more extended conjugation. Because of more extended conjugation, extra stability is given to the enol form even when compared to our previous molecule, right? And what is the second advantage? Yes, it is also having intramolecular hydrogen bond. That's why at the time of equilibrium, now enol content is more when compared to what keto form. And what is the equilibrium constant value? Yes, equilibrium constant value greater than 1, right? For example, if they are asking like this, yeah, two molecules they are giving, and here question is which one forms more enol content? Now tell me the answer. Which one forms more enol content? Either first molecule or second molecule? Yeah, obviously second molecule. What is the reason? Because of more extended conjugation with phenyl ring systems. That's why second molecule gives more enol content when compared to what? First molecule. At the end of this tautomerism, I will give more number of questions on that, right? This is a story about 1,3-dicarbonyl compounds. Yeah, I am going to give one more example. Like this compound is given like this. Yeah, 6-member ring system. Here C double bond O, again here C double bond OH. Slowly I will try to introduce all types of concepts, right? This is my 1,3 dicarbonyl compound. One is in the form of ketone and one is in the form of aldehyde. Now you should remember that whenever two carbonyls are given for tautomerism, now we are using this middle CH. Yeah. Why? Because this is the active CH. What is the meaning of active CH? If it is planked between two electron withdrawing groups, that CH acidic strength is more when compared to what other CH. Very good. Here I am going to write enol form. Here two possibilities are there. You can write enol forms with aldehyde, ketone as well as with aldehyde. Both molecules I am writing, then automatically you will get idea about the stability of these enols. Yes, in first molecule I am using keto form. Yes, OH and right side C double bond OH. This is one possible enol form. Yeah, in case of enol form, you can also use aldehyde without disturbing that keto form, right? Here double bond H and here OH. These are the two possibilities. Very good. I am going to give representations like this: A molecule, B molecule and C molecule. A, B, C. Yeah. Here after writing enol form, look at the stability. Yes. There is a common point, intramolecular hydrogen bond. Very good. Intramolecular hydrogen bond. We know that among all these three, A, B, C, high priority given to but enol form when compared to keto. What's the reason? There is no conjugation and there is no intramolecular hydrogen bond. Least priority given to A. Okay. At equilibrium, at equilibrium, A priority is very less. Otherwise, just I am going to write in terms of what percentages, right? Yeah, almost this existence is 0.2% around 0.2%. Come to B and C molecules, intramolecular hydrogen bond is the common feature in both the molecules. Next, yes, both are having conjugation. Pi sigma pi conjugation, pi sigma pi, pi sigma pi. Yes, pi sigma pi conjugation is there. But if you look at first the B molecule here, there are two hydrogen atoms. These are taken as alpha hydrogen atoms according to hyperconjugation, right? Here also two alpha hydrogen atoms are there. Now these are designated as alpha hydrogen atoms. Clear? Here I have only two alpha hydrogen atoms. Now you tell me on the basis of hyperconjugation, So what we study in hyperconjugation from general organic chemistry, if number of alpha hydrogen atoms increases, then stability of alkene increases or decreases? Yes, increases. Number of alpha hydrogen atoms increases, then stability of alkene increases. Now which is more stable alkene? You observe B and C. Which is more stable and why? B molecule has 4 alpha hydrogen atoms. Yes. And what about C? C has 2 alpha hydrogen atoms. Yes, it is very clear. According to hyperconjugation, which one expected to be more stable? B or C? Definitely B, because of the presence of more number of alpha hydrogen atoms. Around this one, 76%. 76% B, 0.2% first molecule, and remaining C. Okay, that's very, very important. Here 2 enol forms are there. Now B enol content is more when compared to C. B enol content of B is more when compared to what? C. What is the reason? Based on alpha hydrogen atoms. Very important and very simple also, right? Now note on this example. Else, come to next one. Yeah. For example, now this one is very simple. In case of 1,3 dicarbonyl compound, here instead of simple ketone, here I am using ester like C2H5. Then what is the situation? This one also very, very important. Very important example. Okay. This is not simple 1,3 diketone. Yes, one side ketone is present and one side ester is present. Here I am going to write enol form C double bond O C2H5. Otherwise, simply instead of writing enol form, just remember this part. Now in case of tautomerism, so how we are writing enol form? By selecting proton, acidic proton. Yeah. Now just I am going to compare with this keto form 1,3 diketone. Here also Ac2CH is present. My question is, here I am taking HA proton, yeah, and this one HB proton, which is more acidic in nature. Now you know that what is the relation between acidity and stability of anion? Acidity is directly proportional to stability of anion. Stability of anion, yeah. Acidity is directly proportional to stability of anion. Come to first one here, C double bond O. Okay, C double bond O. Once again, better to use same color. Yeah. Now here I am going to remove proton. This is my anion OC2H5. Yes, this is the negative charge. Yeah. After removal of this proton, I am getting negative charge here. Yeah. Once again, what is the relation between acidity and stability of anion? Acidity is directly proportional to stability of anion. Now you look at second molecule. Yeah. After removal of proton, look at stability of anion. For example, if you are asking this carbanion, what about your stability, right? Now it will say that, yes sir, I have conjugation with both carbonyls. Anion negative sigma pi. Yes, there is a conjugation. Negative sigma pi. Conjugation is there, right? Come to first molecule, negative sigma pi. There is no problem with left side carbonyl functional group. Why? Because there is no cheating. It has no any other friends. There is a conjugation between negative charge and pi bonding electrons, or pi system. Negative sigma pi. Negative sigma pi. There is no problem at all. But if you ask right side carbonyl, now here it has 2 lone pair of electron. For example, if I close this carbanion, then what happens here? If I close this carbanion, now this carbonyl says that I have conjugation with lone pair of electrons. Yes, if I close this lone pair of electrons, there is a conjugation between negative charge and this carbonyl functional group. So where we are expecting greater stability, either in second molecule or in first molecule. In second molecule, if this carbanion is asking resonance with this carbonyl, yes, there is a good conjugation. There is no any other conjugated group. There is a direct conjugation between negative sigma pi, negative sigma pi. But here what is the problem? This carbonyl is in conjugation with negative charge as well as lone pair of electrons. Okay. For example, if this carbonyl is spending like out of 10 seconds, for example, if you are taking 10 seconds, let 3 seconds with lone pair of electrons and remaining 10 seconds with negative charge. But here complete 10 seconds with negative charge. Now come to this point again. What is the relation between acidity and stability of anion? Acidity is directly proportional to stability of anion. So where that carbonyl is spending much time with negative charge, either in second molecule or in first molecule, definitely in second molecule, this carbonyl is spending more time with the negative charge when compared to this one. Why? Because here there is a conjugation with this lone pair of electrons also. That's why now this carbonyl is spending less time with this carbanion when compared to right side molecule. That's why now between HA and HB, on the basis of stability of the anion, HB proton acidic strength is more when compared to HA proton. On the basis of acidic strength, now you remember this point. On the basis of acidic strength, here in case of 1,3, dicarbonyl is there but extra ester is present. Now I am writing like this: double bond O, C2H5, and here right hand side I am writing enol form, but here keto form is more dominating when compared to enol form. Very important example: if simple 1,3 dicarbonyl compounds are given, no doubt enol form is better than keto form at equilibrium. But here ester is given. Your carbonyl is part of ester. That is not the free carbonyl. Here carbonyl is part of ester. In that case, keto form is more when compared to enol form because of less acidic strength of that hydrogen. Okay, right. You write same point: due to less acidic strength, due to less acidic strength of CH, less acidic strength of CH in the given molecule, keto content is more than enol content. Keto content is more than enol content, at equilibrium. Therefore, what is the equilibrium constant value? Less than 1. That is a story about a given molecule. Yeah, come to next example. Here I am going to take on the basis of a bond angle strain and aromaticity. Okay, first let me explain about the bond angle strain. Here C double bond O is there. Next, 4-member ring system, double bond O, and 5-member ring system, double bond O. So we know that bond angle strain increases, then what about the stability? Very important point. Bond angle strain increases, stability of molecule decreases. Yeah, that's very important point. Bond angle strain nothing but there is no required bond angle. That's it. Now we know that very simple example. If you are having 3-member ring system, what is hybridization of this carbon atom? Yes, sp3. And outside how many hydrogen atoms are there? 2 hydrogen atoms. What is the required bond angle for sp3? 109 degrees 28 minutes. That is the required bond angle. But what is the bond angle inside the ring system? 60 degrees. Now 60 degrees is present but required bond angle is 109 degrees 28 minutes. So there is a bond angle strain. Whenever required bond angle is absent, then automatically that molecule suffers from bond angle strain. And for sp3 60 degrees, for example, if you are having sp2, for example, if you are writing enol form, what is hybridization of this carbon atom? They are asking question on the basis of enol content. What is the hybridization? sp2 hybridization. For sp2 hybridization, what is the required bond angle? Yes, 120 degrees. But required bond angle is present or absent. Even with sp3 also that much bond angle is not possible. Why? Because with sp3, how much bond angle is possible in 3-member ring system? 60 degrees. But required bond angle 109 degrees 28 minutes. But if you are converting that sp3 into sp2 carbon atom, what is the required bond angle? 120. But there is no required bond angle. That's why your molecule is stable or unstable. Yes, this molecule also unstable. Here the question is, among the given molecules, among the given molecules, which one forms more enol content? This is the increasing order. Increasing order of giving enol content. Increasing order of giving enol content. Once ring size increases, slowly bond angle strain decreases. That's why that is the increasing order of giving enol content. Okay, on the basis of bond angle strain. Let me give one more example. Yes, here I am taking 6-member ring system. Yes, double bond O. Right side there is a 3-member ring system. Yes, write the enol forms and explain the stability. Simple carbonyl is given. Just I am taking compound A. Clear? You have two options to write the enol form. Yes, from left side you have hydrogen, right side you have two options. For example, if you are selecting proton from left side, then what is the enol form? Yes, here OH, and right side what is the ring size? 3-member ring. Let this molecule as B. And come to third one, if you are selecting proton from right side, then what is the situation? Here there is a double bond. Yes, C double bond O. Oh, 1 second. That's not the correct structure. Just 1 second. Yeah. 6-member ring system. If you are using proton from right side, this is the position of a double bond, and outside the ring system there is a OH. This is our compound C. Now tell me this one. What is the stability order? What is the stability order? Stability order. Here there is no concept of aromaticity and no intramolecular hydrogen bond, no extended conjugation, only on the basis of bond angle strain. First of all, if you compare between ketone and enol forms, simple ketone, yes, stability point of view, A is better than B and C. Why? Because in case of enol, no conjugation, no aromaticity, nothing is there. Just we are comparing between ketone and enol forms. That's it. So if you are comparing simple ketone and enol forms, which one expected to be more stable? A. And what about B and C? Now, in case of B and C, now you look at this carbon atom. Yeah. Carbon atom. Around this carbon atom, what is the bonding situation? Yes, there is a double bond. This carbon is expected to be what? What is the hybridization? sp2. Here, what is the hybridization? sp3. Clear? For sp3 hybridization, what is the required bond angle? Required bond angle 120 degrees. We know that for sp3 hybridization, what is the required bond angle? 120 degrees. Required bond angle 120 degrees. In the second molecule, what is the required bond angle? 109 degrees. Yeah, 109 degrees 28 minutes. That is the required bond angle. Actually, the value I am writing here, that is not the actual angle in the ring system. Just I am writing required bond angle. Okay, right. And here for sp2 hybridization, once again, what is the required bond angle? Required bond angle equals to 120 degrees. 120 degrees. Okay. Here sp3 hybridization, required bond angle is 109 degrees 28 minutes. Compared to sp3 hybridization, in this one sp2 hybridization, here required bond angle is 120 degrees. but actually that much bond angle is not present inside the ring system. Compared to this one, here bond angle strain is more. More is the bond angle strain, right? So because of more bond angle strain, your C is expected to be what? Unstable compared to what? B. So if you want to write stability order, right? A is greater than, B is greater than C. Very good example on the basis of what? Bond angle strain. A greater than, B greater than C. Always you remember, if you are comparing with the simple ketones and enol forms, definitely keto form is more stable than enol form. For example, in enol form, if there is a aromaticity, if there is a conjugation, okay, any stabilizing factor is there, then you think about now enol content, okay. In that case, enol content is better than keto, but in this one, directly simple ketone and enol forms are there, okay. So in the second one, sp3 hybridization, required bond angle 109 degrees 28 minutes, but around 60 degrees is there. But here, hybridization is sp2. Whenever sp3 is changed into sp2, required bond angle is increasing, but this much bond angle is not present in that compound. That's why this molecule is suffering from more bond angle strain when compared to second one. That's why what is the stability order? A greater than, B greater than C. Okay, clear. Next one, some important examples are there. Yeah, I'm taking that 4-member ring system. Here I'm taking simple C double bond O ketone, and here double bond O, again here also double bond O. And in third molecule, 3 carbonyls I am taking like this. Yes, double bond O, again here also double bond O. These are the 3 molecules. Your question is, which is giving high percentage of enol? Which is giving high percentage of enol? That is our question. Yeah. So let me write enol forms of this molecule. What is the enol forms? Enol forms. Yeah. So if you are writing enol form, just you write like this, and here OH, that is the enol form. Now here you can use 2 hydrogen atoms for enol. Here double bond OH, next one here double bond OH. That is the enol form. Otherwise you can write A, B and C also. A, B, C. Just for comparison, I am taking like this A, B and C. Okay, fine. And what is the enol form of third molecule? From here you can use the hydrogen atom. Then what is the result? Yes, double bond OH, O, double bond O, again double bond O. That is the enol form. Yeah, from the concept of aromaticity, this is what type of compound? Please tell me what type of compound. This one, non-aromatic compound. Non-aromatic compound. Yeah. Non-aromatic in nature. Okay. In general organic chemistry, we will make so great video on aromaticity, right? Just so directly I am writing like this. I am not giving any rules. Okay. That rules and everything we will discuss in aromaticity. Yes. Non-aromatic compound. And here compound is anti-aromatic compound. Anti-aromatic compound. And what about this one? This one exactly aromatic compound. Yeah. That is the story about enol forms in terms of aromaticity, non-aromaticity and anti-aromaticity. Now tell me this point. What is the stability order in case of aromaticity? Aromatic compounds are more stable than non-aromatic compounds. Non-aromatic compounds. Yes. And least priority given to what? Anti-aromatic compounds. Anti-aromatic compounds. That is the stability order. This is the stability order. Clear? Aromatic is greater than, non-aromatic is greater than anti-aromatic. Again come back to same example. Here after writing enol form, so which is giving aromatic compound? Last one. And after writing enol form, first one is non-aromatic compound, and what about second one? Anti-aromatic compound. This point also very important, that we will discuss in aromaticity. Because of highly unstable nature of anti-aromatic compounds, almost existence is 0. Almost, very less. Almost they are not existing at room temperature. Okay, right. So what is the percentage of enol? Percentage of enol given by the compounds. What is the order? First priority C. C greater than A greater than B. This is the decreasing order. So compound C is giving more percentage of enol when compared to A, and A is more when compared to B. That is the decreasing order of content of enol. Okay. Next example. Yeah. 1 second. Come to next example. Here I am taking 7-member ring system. Yes. 7-member ring system. Here I am taking C double bond O and C double bond O. Pi bond again here, pi bond. 1, 2, 3, 4, 5, 6, 7. Yeah. And what is the second example? Second example, same 7-member ring system, but position of carbonyls are different, right? Here I am taking C double bond O, again here C double bond O, pi bond, again here pi bond. Otherwise you better to take 1 second. Yeah. No, not like that. C double bond O group. You write here. Yes, fine. Last one. Three molecules A, B, C. A, B, and C. Write the percentage of enol among these three compounds. Very good example. Here, what is the ring size? We want only 7-member ring system. 1, 2, 3, 4, 5, 6, oh sorry. We want only 7-member ring system. Yeah. Yes. These two molecules looking like same. Yeah. Yes. Write the example. Compare percentage of enol. Yeah. Percentage of enol. Three compounds are given A, B, C. Which one giving high percentage of enol? First I am going to write enol forms. In the first compound, where from we are using proton for enol? From this carbon atom. Yes, hydrogen, very clear. So what is the enol form of this compound? Same 7-member ring system. Okay. Here pi bond, pi bond. After writing enol form, yes, there is a OH and C double bond O. C double bond O. From aromaticity, we know that whenever this type of compound is given, this molecule comes under quasi-aromatic compound. That we will discuss in aromaticity. This type of compound is quasi-aromatic compound. Okay, quasi-aromatic compound. Now, simply I am taking like this. Your compound is aromatic. Aromatic, and what is the second advantage? It has intramolecular hydrogen bond also. These are the two advantages in enol form. One is aromaticity and second one intramolecular hydrogen bond. Here by using proton from this carbon atom, we can write enol form. Yes, like this. Already there is a double bond carbonyl. Next one pi bond. Here C double bond O. Sorry. COH. That is our molecule. This one also having aromaticity. Now this particular part shows that aromaticity. Okay, right. And come to third molecule, you can use proton from this carbon atom as well as from this carbon atom. You can write that enol form. Again same 7-member ring system. Yes, pi bond. Here after writing enol form you will get OH with a double bond, and here double bond with OH. And what is hybridization of this carbon atom? sp3 carbon atom. So according to aromaticity rules, this compound is said to be non-aromatic compound. Non-aromatic compound. So that is the story about the enol forms. Among these three, two are aromatic in nature and one is non-aromatic in nature. Yes. Then what about the percentage of enol content? How we are expecting? Come to first molecule. Yes, it has aromaticity, but along with aromaticity, what is the extra advantage of this first molecule? A molecule, it has intramolecular hydrogen bond also. Okay, right. Now here there is a intramolecular hydrogen bond. Intramolecular hydrogen bond, H bond. Yes. These are the two advantages. First one, aromaticity and intramolecular hydrogen bond. But in second one, only hydrogen bond. Only aromaticity. It has only aromaticity. And what about third one? Yes, it has a conjugation but non-aromatic compound. Then what is the percentage of enol? A giving more enol content when compared to B and when compared to C. This is the decreasing order. Right? Okay. Come to next example. Yeah. This type of molecule is given. C double bond O, C double bond O H. Double bond O, next one C double bond O H. Just I am giving two molecules. Just tell me which one gives more enol content. Very simple question. First one, 1,3 dicarbonyl compound given, it has CH. And it is flanked between two electron withdrawing groups. And that CH is taken as active CH. Okay. In case of second molecule, there is no active CH. No hydrogen is flanked between, or no CH is flanked between two electron withdrawing groups. Because of more acidic strength of CH, first compound gives more percentage of enol when compared to second one. Okay, right. Here, write one simple question. Question is, which of the following compound gives highly unstable enol form? That is the question. Which of the following compound gives highly unstable enol form? Which of the following compound gives highly unstable enol form? Right? First molecule like this, double bond O, this is compound A. Is it visible? Yeah. Second example, second molecule, this type of molecule is given, double bond O. Okay, right. Compound C, this is our compound, double bond O. And compound D, yes, double bond O, double bond O, double bond O. Now these are the four options given. What is our question? Our question is, which of the following compound gives highly unstable enol form? For example, by using space tautomerism, if you are going to write enol form of this compound, so how can you write? This is our enol form. It is aromatic or not? Yes, it is aromatic. Stable or unstable? Definitely this is stable compound. And come to second one, again you are getting what? Same molecule. Yeah, OH. again it is aromatic in nature, and giving what? Stable compound. And come to last example. Here in this example you are getting molecule like this, double bond O, next one here OH. What is nature of this compound? Now this compound is taken as aromatic compound, okay. And when you come to C, after writing enol form, this is the result, okay. What is nature of this molecule? This one is anti-aromatic compound. Is it stable or unstable? Highly unstable. This is the right option, okay. Very important example. Here among these three, only third compound giving highly unstable enol form. Even same question they can also ask like this: which of the following enol form is not existing at room temperature? Which is not existing at room temperature? This one, because of highly unstable nature, and your compound is anti-aromatic compound. Anti-aromatic compounds are highly unstable at room temperature, they are not existing. Yes. And before leaving this session, one more simple question and important also, right? Here our question is write increasing order of enol content. Increasing order of enol content. Yes. I am taking examples like this: C double bond O, second molecule pi bond, double bond O. That is the question. Yes. What is the right answer? Just you write the enol forms, you will get the idea. What is the enol form of your first compound? Yes. Pi bond OH. Here already there is a pi bond. Extra here you develop the pi bond and you write the OH. That is our enol form. Yes. And here already two pi bonds are there. By using proton from this carbon atom, yes, you are getting enol form. So in third compound, what is the nature? Aromatic, greater stability provided by aromaticity. And first one and second one both are non-aromatic. But what is the different feature? In second compound, it has conjugation between two pi bonds, pi sigma pi. There is a conjugation. And if you want to give the stability order, so where you select, now here let it is compound A, B and C. Which one giving high stable enol form? C. And second priority because of that conjugation, B. And last priority given to A. Okay. That is the answer. C greater than, B greater than A. Next question. Which of the following compound gives aromatic compound in keto enol tautomerism? Keto-enol tautomerism. That is our question. Which of the following compound gives aromatic compound in keto-enol tautomerism? Keto-enol tautomerism. I am giving some options like A, first compound is like this, double bond O, and B is like this, yeah, pi bond, double bond O, and compound C methyl, compound D compound D, okay. And one more example I am giving, compound E, These are the 5 compounds A, B and C. Homework question. If anyone is solving this problem, please comment on the comment box, right? Which of the following compound gives aromatic compound in keto-enol tautomerism? These are the 5 compounds A, B, C, D and E. Okay. So this is our session today, and few more examples are there in keto-enol tautomerism. After completing that video lecture, then I will go to all PYQs. Almost all previous PYQs I am going to discuss. After that only we will go for stereoisomerism. Till then,